Okay, now let us look at the design example for the type 2 member. So, preliminary design of type 2 member post tension beam with flange section is shown below. It has a span of 20 meters, it has uniformly loads and the profile of the CGS is parabolic. MT is 1000 kilonewton meter, the height of the beam is restricted to 1000 millimeter, pre-stress at transfer is 1300 megapascal, at service it is 1100 megapascal, P naught is 1807 kilonewton. This is the previous same problem, we have done the preliminary design, let us say from CU what we get. And we have to evaluate the limiting zone and the stress conditions are FCC allowable is 15 megapascal at both transfer and FCT allowable is 4 megapascal. And at service, this is at service, okay, FCC allowable is 14 megapascal, tension it is 3 megapascal. So, these are different stress limits have been given for both transfer and at service. Now, this is a cross section. I think this is the same cross section that we have been using it for this cross section. Now, it is spanning for 20 meter and it is subjected to a moment of 1000 kilonewton meter, okay, and the other dimensions are given. Let us see now how to calculate my limiting zone. Again, calculations of geometric properties, we have already discussed it, how to do that. So, it is a symmetric section. So, section is divided into 3 rectangles and we got this moment of inertia from previous examples as these values and radius of gyration is this and moment of inertia due to self weight is this. So, it is unit weight gamma w multiplied by the section area and you divide by 10 to the power of minus 12 will give 6 multiplied by 10 to the power of minus 12 will give 6.96 kilonewton per meter. Now, it is simply supported. So, moment due to dead load will be WDL L square by 8 and you get a total self weight moment of MSW or MDL whatever you want to call it 348 kilonewton meter. Now, the E max and E minimum are determined by equating the stresses at the edges of concrete with allowable values. The expression is given like this, okay. These are the internal forces. Stress concept again we are using P by A due to concentric pre-stress due to moment MP which is equal to P into E. This will have negative and this will have positive and due to load this will be positive, this will be negative here, it is all negative. So, the net everything we are assuming that compression that is what we are trying to see. So, the overall in generic way we can write the stress at any point can be minus P by A plus or minus PE into Y by I plus or minus My by I. Now, again depending upon whether it is top or bottom the signs will change. Now, let us using this let us calculate. E max will be governed by transfer condition. Let us say what is the E max. Stress at the bottom because is negative 15 megapascal. So, let us look at all the components. First component concentric component at transfer P will be equal to P naught, right, we have seen that and P naught is 1807 kilonewton that you divide by that. So, and then P naught into E into YB by I is this, E is what we are trying to calculate. So, you put it in terms of E, right, and the next one is self weight moment which is 4.92 megapascal. So, stress at the bottom is going to be compression which should be equal to 15 megapascal. When I put it I get my eccentricity as 535 millimeter. This is a maximum eccentricity that is possible, right, to put so that the C will be always within the console. Now, let us look at E based on the stress at the top. Now, stress at the top also I have to check. Now, this is plus 4, this is in tension. Allowable tension is 4 megapascal. So, let us do the same calculation and if you substitute this is again now it is going to be pre-stressing moment at the top is going to be plus, this is going to create tension, self weight moment is going to be negative, that is why we have negative here. And then when you substitute in the equation and equate to 4 megapascal, you get eccentricity of 592 millimeter. Now, you get two values E max 534, 535 and 592. Which one do we choose? Because we are talking about maximum eccentricity based on the stress at the bottom we get 535, based on the stress at the top 4 megapascal I get 592. Of these two values, you have to choose the lower value of 535, then only for both conditions the stress limits will be satisfied. Because 535 mm is greater than the bottom distance, so we assume a cover of 40 mm and adopt a 450 mm value. Because now you see sectional dimensions itself, your CG is having only 500, so I cannot take eccentricity more than that. So somehow, or what we can do is you can reduce the flange width and I can increase the depth, but architectural reason says that I cannot go more than 1 meter. So even though this is allowing me, so I have to restrict it to 450 mm of eccentricity as per this condition. Now let us look at minimum eccentricity based on the service condition. Now E minimum, again stress at the top is in compression, which is 14 megapascal. So effective now it will become P will become effective pre-stress, right. We take 85% of P naught, so that divided by A 5.29 and P into EYT by this is this, and then live load moment is this and self-weight moment is this. So you see here at the top both live load and self-weight will create compression, negative, concentric pre-stress component will give negative compression, only pre-stressing due to moment component of pre-stress will create tension, that will be plus. So you equate everything to negative 14 megapascal, then you find the value of V, that works out to be 250 millimeter. This is again based on the service condition for stress at top. Now we need to do the same thing for stress at bottom, which the limit value is given as 3 megapascal. So again we go through the exercise. Now the pre-stressing will produce negative, this is going to be compression, right. The live load is going to be tension, positive, and self-weight moment is going to be again positive, right. So this is self-weight, not this, 4.92 is self-weight, positive tension, negative compression, that equate to FB equal to 3 megapascal. So if you equate that, I get eccentricity of 269.42 millimeter. Now again we got two values, which value will you be choosing? So you have to choose 269 and 250. This is based on the bottom tension, this is based on the top. Now which one would you be choosing? So you have to choose here higher value of 269, then only for both stress conditions will be satisfied, right. So in this way you see here E minimum is 269.4, E maximum is taken as 450 millimeter. This is for section at midspan. Okay, so these are the values that we are getting, right. Now let us say what is the limiting position at support. At support, simply supported, the moment component is going to be 0. So I have only pre-stress, concentric pre-stress and pre-stress moment due to pre-stress. So if you put the same equation that what we derived, only the moment component will not come, then you will find that eccentricity at transfer, I have to choose a lower value of 342. This is again based on the stress at bottom, stress at top. From the same equation, put moment equal to 0 and then use allowable values and get your two eccentricities. Of the two eccentricities, I need to choose E max as the lower value, okay, for transfer condition. E max will be always the lower of the two values. Similarly, at service, we will define the E minimum value. The stress limits are 3 megapascal at tension, at bottom and top it is negative 14 megapascal. If you substitute both of them, I get a negative values of eccentricity. What is the meaning of negative values of eccentricity? That means eccentricity can be above the CGC, right. So that is what the meaning is. So CGS lies above CGC. The position of the CGS is closer to the CGC selected. So E minimum I am taking as 381.15 millimeter. That means whatever is closer to the CGC that I select. So if you plot this, this is the way it is. At support, you see this is the limiting zone. Okay. So, in this area I can put my CG of the strand, then I will satisfy my stress limits which are kept here, right. So, you can say that the limiting zone tendons can be spread out at the ends. That helps to reduce even stress concentration, because you will be anchoring a lot of cables at the end. So, if you have a larger region, it is better always. Anchoring the tendons at the end plays a crucial role in reducing the stress concentration at the ends, right. So, if I have a larger zone, it helps me to reduce the stress concentration to avoid the splitting cracks that typically happens in post tension elements, right. Now, detailing requirements. So, let us spend some time on what are the minimum requirements from detailing point of view. So, first let us talk about amount of reinforcement, tendon profile, and some miscellaneous requirements that are given in IS. Predominantly we have taken from IS 1343, but some additional requirements can be there from IRC as well. Okay, what is the minimum longitudinal reinforcement? So, they should always, minimum steel should be provided, so that they are going to have sufficient strength after cracking. If you put very little longitudinal steel, after cracking, if the energy release is so high, then the strand or a steel can rupture quickly. So, we do not want that rupture. So, that is the reason always when you calculate your M ultimate should be higher than 1.2 times MCR. So, from this we get my minimum longitudinal steel. Okay. According to the section 19.633, the minimum steel for both ASP and AV is 0.2 percentage of your area. It is not very high, right. So, the minimum together, the pre-stressing and non-pre-stressing steel, if I add them up, that should be at least 0.2 percentage of your overall cross section area, right. So, this is very nominal. Similarly, ACI, if you look at it, the minimum amount of non-pre-stressed steel is 0.4 percentage of AT. Now, what is the area of AT? The definition you see, it is a tension area below the neutral axis. So, in a way, if you assume this AT to be half of what for the overall area, then it goes back to your 0.2 percentage what we had it in the previous slide. Okay. So, again, this above reinforcement is not really intended to provide flexural strength. So, if you see here, when you have an unbonded system, typically you will have this kind of a crack, large crack which is possible. It is possible. In case of a unbonded tendon with the non-pre-stressed steel, what I can do is I can put, instead of one major crack, I can have lot of multiple minor cracks or smaller cracks that will help. So, you get a better crack distribution and better performance, especially when you have an unbonded steel. You should also put some non-pre-stressed steel of some nominal value. That is what the code is saying, the ACE code, which should be 0.4 percentage of your tension area. Okay, so that is what it is, AT. So, AT is nothing but this is the area. Okay, this area is what we are talking about. Now, what is the side face reinforcement? And if you see here, when the depth of the web exceeds 500 mm, a minimum amount of longitudinal reinforcement should be provided on each face of the web to check the thermal and shrinkage. Otherwise, shrinkage cracks can become small, form, and then finally it can convert itself into a structural crack. So, section 19.633b, they tell you the minimum side face reinforcement as 0.05 percentage of your area of your web, that is a vertical area. It is a very nominal reinforcement, and typically good idea is to put smaller diameter, so that you get little closer spacing because the cost of the steel is always function of the area of the steel. If you use smaller diameter, if you reduce the spacing, it will give you always much better performance, but again the spacing should not be too small for the concrete to flow, So, that is the reason the maximum spacing of the web bar is typically limited to 200 millimeter. Cover requirements from fire resistance point of view, from durability point of view, always we need to have minimum clear cover of concrete, protect against corrosion and to develop adequate bond between concrete and steel, and also from fire resistance point of view, that the cover is typically implemented by chairs or cover blocks. And if you see section 12.16 For pre-tension members, the minimum cover is 20 millimeter. For post-tension members, typically the center of the sheathing is at least 30 millimeter or size of the tendon. That much cover should be required. And minimum cover should also be increased by 10 mm in case of an aggressive environment. These are all the some of the guidelines for the cover. What are the spacing requirements between the ducts? A minimum clear spacing for the tendons or reinforcing bars is necessary for the flow of concrete during casting and to have adequate bond between concrete and steel. Now, if you look at section 12.17, the minimum spacing requirements are as follows. Clear spacing, that what we have given here, should be greater than 3 times the wire diameter, and it should also be maximum of greater than one third of your maximum aggregate size. So, if you are using nominal size of 20 mm aggregate, 20 into 1 third, right, should be your spacing. Spacing should be greater than this, right, 20 millimeter I should say. And for large bars and tendons, the clear spacing should be more than 40 millimeter, or maximum size of the tendon or bar, or maximum aggregate size plus 5 mm. For a grouped tendons like this, the requirement for spacing between the groups is like this. So, this is the horizontal spacing, this is the vertical spacing. This should follow this clear spacing. All the 3 conditions it should satisfy. Okay. So, you take the maximum of these values. Okay, that is what it is. Minimum spacing, again horizontal spacing should be as we given in the previous figure as per section 12.18. Horizontal spacing should be greater than or equal to 40 millimeter, or maximum aggregate size plus 5 millimeter. Vertical spacing should be greater than or equal to 50 millimeter. Now, the pre-stressing steel also has to be anchored well. In a partially pre-stressed section, when non-pre-stressed reinforcement contributes to flexural strength, the development length of the bars needs to be checked. Always the development length has to be checked. LD is, we will talk in when we talk about bond aspects, typically written as function of 30 or 40 times diameter of the bar. Something like this. Always is written as a function of your diameter of the bar. And the bar should be anchored at supports by hooks to avoid anchorage failure. Otherwise, the bond, adequate bond will not be developed, and the slippage of the reinforcement will happen, and it may lead to premature failure. So, bars also need to be anchored well. Tendon profile. In case of a post-tension system, again tendon profile, it has to be done in a proper way, and this is a typical for a 2-span system that we are talking about. So, we are saying that it should have a 0 slope at the point of maximum eccentricity. For example, here, slope should be 0. At a point of contraflexion, the slopes of the parabolic segments on both sides should match like this. Okay, this and this should match, and that is expected. The convex segment over a support is required to avoid a kink. Always over the support we need to, you cannot have this kind of a sharp cable. Always you need to have a smooth cable like what we have, smooth transition we should have. Okay. So, convex segment over a support is required, and the length of the convex segment is determined based on the minimum radius of the cover, that what we talk about, okay, of the section. Now, sometimes this also in the very beginning of the semester, the beginning of the course that we talked about, the tendency of the strand inside a duct will be at the maximum, the sagging moment location, midspan location, it will tend to move up on the upward towards the duct, but at the high points it will try to move. In that way, the overall eccentricity will reduce. Some corrections have to be done. So, the corrections have been already given in the tabular form, and we need to be very careful of that factor. So, this especially when you talk about a 19 strand or a 27 strand, your duct size will become bigger. Okay. So, in that case what will happen is the small reduction in this movement or eccentricity also will play a role. So, that has to be accounted. Typically the manufacturers will give me what should be the correction factors for the eccentricity, right. These are some of the very important detailing requirements. So, let us summarize what we have discussed in this part of the module. In this part, we have explained the concept of flexural design for type 1 and type 2 members. We also talked about limiting zone, how to calculate the limiting zone, and we also learnt about various detailing requirements for pre-stress members, right. So, with this I think we are completing this part of the module. Again, one more module is there. There we will talk about the graphical method, Magnell's graphical method of design. Alright, thank you.